Evening. Um, Thank you so much, Marion, for taking your time and presenting this use case for us. And this is going to be this is going to be really good. So I think over to you. We're over time, and I think Marion, you could introduce yourself and then start with the session.
Sure. Yeah, thank you. I'm very happy to be here and to be talking to you all about what I do on a day-to-day basis, basically. Well, not all of it, but in general. So yeah, I'm a PhD student at the University College Dublin, and I work on gender bias in language models or in natural language processing more broadly. And today I'm going to be talking to you about assessing gender diversity in texts. And I have a notebook prepared that I'm going to share now. All right, I hope this is going to work.
Marion, could I interrupt you for a
Sure.
minute? Is the recording started already?
I think it is, yeah. Should be recording.
Okay, that's good. Thank you.
Okay. All right. I hope you can see my screen now.
Yes, we can.
Okay, Grant. All right. Yeah, assessing gender diversity in text. So basically I've divided this into two parts. The first part is about analyzing word frequencies. So this is going to be very basic. We're going to take a text corpus, tokenize it, and then do a little frequency analysis of pronouns and address terms. And in the second part, we're going to be analyzing vector representations and building a word-to-vec model with the GenSim library. And I'm also going to introduce this a bit more in detail later on, because I know, like last time, Lilia talked about vector representations, and this is a different kind of vector representation that she didn't get to. So yeah, we're going to talk about that, and then analyze some word similarities with that. All right. Yeah, so we're starting with the setup here. So basically just importing all of the necessary libraries, and I'm gonna run this notebook from here. Yeah, so we have pandas, numpy. We're probably going to use pandas later. Then frequency distribution to do the frequency analysis from NLTK, which is the Natural Language Toolkit library, a really important one in natural language processing or text analysis in general. And then here, the GenSim library to build the word-to-vec models, the datasets library from Hugging Face, which kind of allows us to download a bunch of different datasets quite easily. And then there is tokenization, actually sentence tokenization, we won't be using that one. And then TQDM is just to show a progress bar, so you'll see that later on. There's the random seed, so we're going to be doing some shuffling. That's why we need randomization there. Yeah, so the data that I chose for this notebook is a small portion of the Common Crawl news dataset, which is available on the Hugging Face datasets library. The Common Crawl is it's a very big dataset. It's basically a crawled version of texts on the internet. So it's very, very large. And then this portion just contains news articles. This dataset is comprised of about 700,000 English language news articles. They were published between January 2017 and December 2019. So reasonably old or young, depending on your point of view. I'd say, yeah, it's definitely a little bit old, but it's also not too old. Yeah, so gonna be running that, and then it's very easy to load it with the load dataset function from the datasets library, and then we can have a look at the dataset. And here, as we can see in the training portion, so you have to specify train, test, and validation. In this library, we only have this training portion. So basically, this is not about training or testing validation. So they just have this one. This one whole big data set. And then we can have a look at the features of the data set. So technically we have a title, the text, the domain. So where this is from, then the date that it was written, a small description, URL, and if there were images in the article, there's also the image URL. Right. Going on, just to have a little bit of randomization here when we're training our vector model later, I'm going to shuffle the data set and then also reduce the data set further to speed up training later on. So as you could see here, we have 700,000 articles, but we're just going to take the first 100,000 articles of the training portion, so of the general data set. And we're also just going to take the texts and leave the titles. Yeah, just we're not going to use them because this is already a lot of data for my little machine. Okay, so, and then this is taking a while because it needs some time to separate the data. And then I'm also printing the length. So just to make sure that it was really the first 100,000. And then we're having a look at a small example. So the article number 57. And we can see, okay, it's about Oklahoma City and the FBI and so on. So yes, this looks like a news article. And then once we have this data in this news text variable, and we can access all of the different articles, we can go on further to tokenize the data. I know Olivia talked about this later on, but basically what we're doing here is we're applying the word tokenize function from natural language toolkits from NLTK. And just to show you what this does, I applied it to the news texts here, or to number 57 of the news texts. And here, so the word tokenizer takes this, which is a string, and creates a list of strings, so a list of tokens. So here you can see them side by side. You can also see that it separates these brackets, for example, and that punctuation is separated. And then like that, later on, if you had a different task for machine learning, you could filter out those punctuations, or you could normalize the data, but we're not going to do all of that today. We're just going to take the data as it is and see where that gets us. Yeah, so basically here I tokenized just one example, and I'm gonna, yeah, okay. And then we're gonna apply that to the entire data set. So with the TQDM, that just shows a progress bar. Actually, I should have pressed that before because it's gonna take about 3 minutes to tokenize the first 100,000 articles in our data set. By the way, I forgot to say this before, but if you have any questions, do feel free to put them in the chat, and I hope I'll see them. And if not, please, you can also just unmute yourself and ask questions along as we go. I hope I have some time at the end to answer questions, but yeah, just as a reminder, feel free to unmute yourself and ask a question when you have it. Okay. So yeah, this is gonna take a while, but I can walk you through the next couple of steps while this is running. Yeah, so now we have all of our articles, they're tokenized. And once we've done that, we can have our first exploration. So basically, the frequency exploration just looks at which words appear how many times in the text. And since this is gender focused, we should be looking at words that denote some sort of gender. So pronouns, for example, in English, either there's masculine, feminine, and gender indefinite pronouns. So masculine pronouns here would be he, him, his, himself, and then feminine be she, her, hers, herself. And then we have plural pronouns like they, or themselves, which can also be used as gender neutral pronouns, or the preferred pronouns of non-binary people, for example. But here it becomes really tricky, because if we're just looking for the pronoun they in text, then we don't know whether the use is as a plural pronoun or as a non-binary pronoun. There are some some programmatic approaches that kind of either take the syntax of a text into account, so like the sentence structure, to infer whether we're talking about a single person or more people. But this is a bit too into too much detail for this type of workshop, so unfortunately I can't talk about that today. But yeah, we're gonna look at these 4 pronouns and the masculine and the feminine versions. Yeah, we're gonna count them. So we have this count dictionary, which has 1 key masculine, 1 key feminine, and then these dictionaries are just gonna hold how often each of these pronouns occur in the text. Yeah, this is still taking a while. I thought it would take 3 minutes, but it has already taken 3 minutes. Okay, but nothing we can do here. That's a bit of the trouble, because WaiTUTORIALs here from NLTK is, in my opinion, it's a good tokenizer, or it's a good tokenization program, but it's not necessarily optimized for speed. That's why this has taken a while. We're at 30,000 of 100,000. Okay, so this should take another 10 minutes. Okay, let's see. I'm just gonna go through this here, and then we can run them afterwards. Actually, I'm gonna be running them as we go along. Sorry about that now. Yeah, so first, once all of this is tokenized, we're gonna get all the words. So this is a list comprehension here that goes through all of the tokenized text, all the articles in the tokenized text, and then takes all of these words in the articles. So instead of having a list of articles, or a list of words, we just have a simple list of words. So all of the words that occur in the entire data set. And then we can apply this function frequency distribution to this. And then basically this function is going to count all of the words for us. So each word becomes a key, and then the count of that word becomes a value. So we can query this frequency distribution like a basic dictionary, basically. And it also has this nice method here, most common. So it shows the most common 30 words. For example. Yeah, so here we would go through the words and frequencies and then print them out. Can't do that yet. Where are we? Almost at halftime. Great. Okay, and then the next thing is we're gonna put them into the count dictionary. So for masculine and feminine, get all of the pronouns, and then put them into the frequency distribution, and we can display them here in the count dictionary. Right, and then I've written some code to display them a bit more nicely, and we're gonna have a look at them once it's run. Okay, where are we? All right, half of them. So it should take another 5 minutes. Okay. Again, sorry about that. I thought the last time I ran it, it took 3 minutes, and this time I think my computer is a bit more busy. All right. Again, okay. There is some results here, but I think it makes more sense to look at that when I actually have the numbers. All right, okay, so and then this kind of creates a plot which shows the counts a bit more nicely. The second analysis that I've prepared here is with address terms. So instead of, pronouns are one way of expressing gender through language. Another one would be address terms, but yeah, basically this analysis you could do yourself at home. There are other words that denote gender, such as even the words woman, man. So these are gendered words, but also first names are an indicator of gender. So how often the word Mary is used in a text as compared to the word John, for example. Yeah, with address terms, we need to take care of this difference of the different spellings. So we have the American spelling with Mr. with the dot here, and then the British spelling with just MR. And then also we have a difference in the expression of marital status because address terms for women that are used still denote the marital status of women, even though we already have the MS, which would be the equivalent to Mr. So here we have Ms. With the dot and without. Then we have Mrs. for married women and Miss for unmarried women. And then there is also here we can actually have we could have a look at non-binary gender, or we're going to try at least. So some people that are non-binary would use the address term mix or MX to basically not choose between Mr. or Mrs. Yeah, this is an address term commonly used by non-binary folks. And then we're going to do the exact same thing as before with the pronouns. So you have the masculine, feminine, neutral, and then putting all of the counts here in this dictionary. And since technically we have the frequency distribution, we can just query that again like a dictionary and then put the items in here. And I'm basically rerunning the same code here. I would be if I had the tokenized text. Yeah, and then kind of displaying it nicely. And yeah, and then we could see some gender differences in our corpus. Let me go back and have a look. Okay, almost here. Almost made it. 78,000 from 100,000. Okay. Yeah, this is very interesting because it kind of also points at a problem that we have in natural language processing or text-based AI in general, is that the newest models that are transformer-based are trained on gigabytes and actually terabytes of data. And that not only takes a lot of processing power, but it also takes a lot of time and time and processing power. So yeah, especially if you don't have the best processing power available to you, like Google, Microsoft will all have data centers to run these big models like ChatGPT on, which are all text-based, and you're stuck with your own little machine, then this occurs more often, and you can't just analyze as much text as you would like to in order to kind of gain an overview of what is in a data set, because you wouldn't use that time to actually train a model instead of looking through all of it. But yeah, that's just a little aside while we wait on these data to process. Okay, so
Sorry, Marian, I think somebody is typing here. I cannot unmute everyone there.
yes, I hear that too.
I think now, can you hear me?
Yeah, I can hear you loud and clear.
Yeah. Can you mute yourself? I think your typing is coming in like as noise here.
Right, sorry about that.
Yeah, no problem.
Okay.
Thank you.
Sure. There. Okay, let's see. Almost made it. We're almost here. That's great.
Yeah, while we finish it, Marian, if I could ask a question.
Sure.
Do you have you used any other tokenizer in this context? Like, I know that this is word tokenizer, and there are other kinds of tokenizers in NLTK.
Yeah, in NLTK, I've not in this context, but I've used the tweet tokenizer, for example. So there are different tokenizers that are trained to specific purposes, and I know a lot of, for example, marketing analysis would use social media data. So here you could use the tweet tokenizer, which deals a little bit better with special tokens like the @ symbol, you know, for usernames and hashtags and stuff.
Oh yeah, right.
Yeah.
Okay, thanks.
Yep. Okay. So let's see. Basically, here, you know, we had example number 57 before, and now all of the text is tokenized. And now I want to print the same text again, just to see that everything worked out okay. Okay, but it's still running the flattening of the list of words, so the getting the list of all the words. Right, okay, so this is also gonna take some time. All right. Here we go. Here, all right, number 57. Yeah, looks the same as this one. So that worked fine. So we have all of our tokenized text, and now we also have all of the words, and we can create a frequency distribution here. And then print the most common words. And here we see that the most common words are comma, the, dot, so like full stop, to, and, of, a. And this is actually what phenomenon that Lydia was talking about yesterday. So these would be the words that occur most, and they are mostly their purpose is mostly grammatical, so that the sentence makes sense. Like if we saw these, this distribution of words would be the same for all or almost all texts. So that's what we call stop words. So if you do some general machine learning, like some classification with text, you would probably want to filter out those stop words because they're not very informative as to what a document is about. But yeah, this is just how words are distributed. So the ones that are grammatical are usually the ones, or have a mostly grammatical purpose. They're usually the ones that occur most often to create grammatical sentences. But we still have all of the counts of the pronouns. So you probably could see what this was about before. So we have the pronouns, the masculine pronouns. He occurs about 155,000 times. And she occurs about 60,000 times. So there's a big discrepancy in this corpus. If you remember back what this corpus is about, it's news articles from 2017 to 2019. We can display them a little bit nicer, or even as a bar plot. But yeah, so basically what these show is that these news articles talk a lot more about men than they do about women. And this is the discrepancy that you can find in a lot of data sets. And if you're working with data yourself, I would invite you to do this very simple analysis for yourself and just have a look at how gender in your data is distributed, because it might influence the way you're working with it downstream. So we have more masculine and feminine pronouns. So feminine pronouns make up about 28% of all of the pronouns. So that's less than 1/3 of gender pronouns in the data set, which is not a great distribution. And we can, name plot is not defined. I think I missed one here on the imports from, no, sorry. I think that's import match. Yeah. SPLT. I think it's matplotlib plot. Yeah. .pyplot?
Pyplot, yeah.
Okay, thank you. I was going through it before cleaning those up and I must have missed that one.
Mm-hmm.
Okay. Here we go. Yeah. So here you can kind of see this, you see this in the plot. So this is a bit more visual than just having the counts. Yeah, we can do the same with the address terms as I talked about before. So here we'd have a frequency, use the same frequency distribution and see them a bit more nicely. So here we have about 40,000 counts of Mr. with a dot, and then 4,000 counts of Mr. with dot and 8,000 counts of Mr. without. So about 12,000 counts here. And I'm not going to do the math myself here, but I'm going to let this do the math for me. So yeah, we have about 12,000 address terms or masculine address terms and 5,000 feminine address terms, which basically shows the same difference than the pronouns before. And again, it just shows that yeah, in this news data set, that women's issues are underrepresented compared to men's issues, or yeah, there's just a lot fewer mentions of women than there is of men. Yeah, and this is, as I said, this is the Common Crawl data set, or is the news portion of the Common Crawl data set, which is a it's a data set used in, or at least the Common Crawl is used in training ChatGPT. And this is just, I think this is an important factor to keep in mind. Right, so now that we've looked a bit into frequencies, let's look a bit into meaning, or into representations in the entire corpus. And yeah, last time Lilia talked about vectorization, so basically like this. So we have a document here and we turn it into a vector by counting how often or if the words in the vocabulary, so all of the words in all of the documents, if they occur in this one document, and then we can create a vector based on that and turn a document into machine readable format like that. Instead of using, oh yeah, thanks for the comment, Nabanita. Thanks. That's great. I agree that this should be included in dataset analysis.
Yeah, I never tried that before. I've worked on these few data sets before, but then yeah, this is great analysis. Yeah,
and it's very quick too, technically.
Yeah, I can see that.
Yeah. Right. Anyways, so here we have these documents, and we can encode them like vectors like this. But in, I think it was 2018, word embedding models came up, or no, sorry, 2013 actually. Yeah, word embedding models came up that were able to represent not just documents as a vector and thereby a machine readable representation, but words. And so here's basically the difference. You can also say like one-hot vectors, you could think of them as TF-IDF vectors or count-based vectors. So instead of having one here, you would have how often the term occurs, or how often the term occurs in relation to other terms in the dataset. But yeah, in word embeddings, basically these are learned representations for single words. So here you'd have all of the vocabulary that you can specify before. So you can restrict the vocabulary of your corpus, and then basically just, for example, include words that occur more than 5 times. So words that are actually frequent in your corpus. And this algorithm called word2vec would set the size of the vector. So here, I don't know how many columns these are, but usually the vector size is, for example, like 100 columns, or 128 or 256. Yeah, you can set the size, and then this model learns representations that make sense later on, because you could also imagine these vectors as points in space. So there would be a point for man and a point for king, and then the relation of them, so the distance between them, would be informative. So you could see that woman and queen have the same relationship, or they have the same approximate distance as man and king. And here you could, like this, you can represent semantic relationships, so relationships that relate to meaning of the words. Not only meaning of the words, but also grammatical properties of the word. So here you would have the ing form of these verbs, and then the past tense form. And yeah, this is also the same relationship between the words, and this is represented in space as well. So you could have similarity based on the grammatic properties of the word, but also the meaning properties of the word. Yeah, this is some similar things. So you have all the countries here, and then these would be the capitals, I think. Yeah, that the model would infer based on, if you give it the Spain-Madrid relationship, and then say what's the same relationship with Italy, then it would give you Rome. And we can do the same thing. So first of all, we have our tokenized text here. And then we can train a model. I set the vector size to 256. It's always useful to set it to powers of 2, just for processing reasons later on. But basically, you can choose any size you want here. The window is 5, so that means that it looks at 5 words before and after the word that it's currently looking for. So basically, it gets these vectors by predicting which word is before and after. Sorry, what is the word in a context? So if there's words before and after, and there's the gap, and then it predicts what goes in the gap. I'm not going to go into too much detail on this. There's a lot of good tutorials online, but basically I want to just show you what you can do with these vectors, also in terms of gender analysis. Again, this will take a couple of words. That's why I'm going to go through the code. Sorry, it's going to take a couple of minutes. So I'm going to go through the code first. Yeah, so basically what we're going to do is we're going to measure the similarity of words, or word vectors to be more precise. And the vectors can have a similarity range from 1, which is very similar, to -1, which is very dissimilar. And 0 is kind of in the middle of, yeah, you could also already say that these are not similar. There's no relation. And then if you have -1, there's like absolutely, these are not related. Yeah, so here, this model, this word2vec model, has this method called word vectors, and then you can get the most similar words to a given word. For example, computer, and you can specify how many words you want. So I specified the top and 20, or so the top 20 words, and you can then I would run this once the model has trained. Yeah. And then there is some other examples. So there's, on one hand, there's most similar, but you can also take 2 words and see how 2 words are similar. So here I have the word help and zebra. And then I also looked for cat and dog. And I hope this is not going to be another tokenization thing, because the time is running out. Yeah. But we can also, so once we have these similarities, I'm actually gonna give you the results now, because I've run this before. So help and zebra obviously are not related, so we would have a negative similarity there. And cat and dog are both pets, both mammals, and used in similar contexts. This is actually the important part. They're used in the same way in sentences. So that's why they're quite similar. But we can also check similarities that are inferred from the corpus and that kind of rely on gender stereotypes. So here I checked for the similarity between woman and makeup versus the similarity of man and makeup. And this would be the stereotypes of, that women, I don't know, are more associated with makeup. I'm not sure that you could call that a stereotype, but I think you know what I mean. But this basically looks at the association between these two words, how similar they are, how often they occur in the same context in the corpus. And you could also do the same thing with woman and angry or man and angry. And then you could see here that woman has a stronger similarity to makeup than man does. And woman here would have a less strong similarity to angry than man to angry. Because although this difference between the two angry things is not that pronounced. So I would also caution you, so if you do this kind of analysis, yes, we can look at stereotypes that are ingrained in the corpus that then become ingrained in the model, but we shouldn't overinterpret into these things. So if there's a minuscule difference between the similarities, that might not be that indicative of the stereotype. Okay. And then, and the results might not always confirm the stereotype. So I looked at woman and professor and man and professor because I thought probably women would be less associated with the academic professions than men, but actually here the similarity between woman and professor was higher than between man and professor. And this just kind of shows you that this is also corpus dependent. So the model is trained on a specific corpus or on a specific data set, and the associations that are in this data set are going to be in the model. And then there's the analogy task. So basically what I've shown you before, woman, king, man, and then it comes up with queen. But again, this might not always be accurate because here, if you have Ireland and Dublin, and then I would have the country France, and I would expect the analogy result to give me back Paris. I think the result was actually Edinburgh. So especially if the model is not trained on that much data, which is the case here, and you would say, okay, maybe 100,000 news articles, that sounds like a lot of data. It's not, unfortunately. There is some meaning captured in it, but in this case, it's always the models are gonna be more informative if there's more data. Okay, there's a question now. Stereotype means that word 1 is often associated with word 2 in the data corpus. Is that trained on? Yes, exactly. So here, if you would have woman and angry and man and angry, actually I can run this now. So here with the similarity basically means that woman is often used in the same context as women and angry are used in the same context less often than man and angry in that sense. Yeah, okay, I hope this cleared things up. Great. We can also run the women and makeup, and this is actually a stark difference. So here you could see that women and makeup are more closely associated than man and makeup. So here you have those results for professor. So it's not that much of a difference, a bit like here with angry. So we might not want to overinterpret into this. It still comes up with queen for woman, king, man, queen. And here, as I said, Limerick. Okay, so it's another city, even though it's in their own country. Okay. Yeah, and this is basically also another way of looking at gender representations in your corpus, and I think I'm definitely out of time. If you have any other questions, feel free to unmute yourself or pop them in the chat. But yeah, this is the end of my talk. And thanks so much for listening.
No problem. Thank you so much, Marion. If you have any questions, please write in the chat, or we'll be more than happy to, talk to you if you want to unmute yourself. I think that would be great. Okay, I don't see any questions, but Marion, I just want to thank you so much. But I think this is a very different kind of use case, and I'm very much used to using all these technologies, like all the different libraries that you're using for vector representations and getting similarities using word-to-vec algorithms, but I never kind of looked at it from this angle. So I think this is really great work.
Thank you.
Thank you so much.
Thanks. Yeah, it was a lot of fun.
Yeah, it is. It is. I could see that.
Yeah.
Can I see some of the results again, please, from the similarities?
Oh yeah, for sure.
Clearly, that's very interesting. I think there's loads that we can do from this.
Oh yeah, for sure.
Interact from this, yeah. Have you worked on any other data sets apart from this, which is more like maybe related to corpus, which is related to sort of identifying gender stereotypes, or
actually I've just downloaded this one for this tutorial. Usually I've worked before with a corpus that is outgoing Reddit links. And the corpus the last time I worked with was about 32 million words. I haven't done the word count on this one yet. But yeah, so the pattern that you could see here with, for example, the frequencies, yeah, I've seen that before. That there is about 1/3, like women are mentioned about 1/3 of the time, and then men 2/3.
Oh, that's interesting.
Yeah. Yeah, I'd love to see the results that would be different for a, more stratified corpus.
Yeah. But I think, yeah, I think the focus of this analysis is to not look at stratified corpus, I think. Because that's just going to remove all the bias but we're trying to see if there's any kind of bias, I think.
Yeah. I think there's two kinds of bias. There is the one like the one that you could see with the frequencies, just the mentions. That's one kind of bias. But then the meanings that this model learns from the context is the other kind of bias. And even if the corpus were stratified, I'd still say that there is, for example, the similarity of women in makeup. I think you could still retrieve that even though the mentions would be the same.
Right, that's true. That's true.
Yeah.
But are there any questions in the queue as well? No. So if there are no more questions, I think we can wrap up this session. Thank you so much, Marion. Like I said, this has been really interesting for me and really insightful for someone who's been using it, but then this is a completely different perspective that you've opened up in front of me today. Thank you for all your hard work, and thanks everyone for joining this session, and see you in the next one. All right. Have a nice evening, ladies, and
thank you.
have a nice weekend.
You too. Bye-bye.
Thank you.